So let's talk more about these orbitals and what their shapes are like. I really need to look up. Does anybody know the name of that Greek letter? It's not omega. Well, I think it's phi. Phi sounds right. Phi squared. So phi squared, and if I'm wrong, just deal with it. That guy squared is the probability density. The probability of finding an electron at a point in space. So if we take phi squared, this is the probability divided by the unit volume. Okay, so the s orbital is spherical. When we solve Schrodinger's equation with n equals 1 and L equals 0, which corresponds to the s orbital, and then m sub L is 0, the shape that we get is a sphere. The probability density is going to decrease as the distance from the nucleus increases. We're going to look at some plots of this, and the plot resembles multiple exposure photographs. So that's like, you know, taking a snapshot of Andrew in the house, like I drew with the yellow, orange dots, right? It's like every 5 minutes, there he is, there he is, there he is. And so you get clusters of dots where things are more populated. It's important to understand that the electron is not moving around the nucleus like a moth around the flame. It's not just kind of zinging around. I sometimes think of it that way, just, you know, random like Andrew. It's not really doing that. Really what it is more of a standing wave. In a sense, the electron's location is spread out over the entire volume of the orbital. In a sense, it's everywhere, and yet it can only be in one place at a time too. And that's that whole quantum duality thing, right? How can it be a particle and a wave at the same time? A wave can occupy all of the space at the same time. I think I have a video of standing waves, and I'll show it to you in a minute. So this would be like a multiple exposure photograph. If, okay, the electron's there. Okay, we took a picture later, the electron's there. We're just catching it in different places. And so we could say that, you know, I think they do this at 90% probability that it's within this area. But when we graph the probability density, psi squared, what we see is as the radius, the distance from the nucleus increases, the probability falls off. And so this is telling us that the electron is most likely found at the nucleus. But that's not true. It's not stuck to the nucleus. It's around the nucleus, but it's not on the nucleus. And so there's something not quite right with this. And so what they do is they use a radial distribution function. This represents the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. And if the math is going over your head, just let it go. This gives us a better picture of where the electron's likely to be found. So it takes total radial probability, takes the probability per unit volume that we graphed earlier, times the volume of the shell at that distance. As you go out from the nucleus, the volume gets larger. At the nucleus, the volume is going to be very, very small, and so then the radial probability is also going to be very small. So we've got these two different, we've got two functions with opposite trends. The psi squared has a maximum at the nucleus, decreasing with r. The volume of the thin shell is 0 at the nucleus and increases with r. And the result is we get a plot like this that predicts that the electron will not be found at the nucleus, and the probability increases as you go out. It reaches a maximum here, and then it falls off again. So this predicts that the average distance from the nucleus for an electron in a hydrogen atom is 52.9 picometers. And that's the same radius that Bohr predicted from his model. But there's an important conceptual difference. In Bohr's model, the electron is always at 52.9 picometers. It's orbiting, traveling in a big circle, always the same distance from the nucleus. In the quantum mechanical model, the electron is found at various radii, but 52.9 is the most probable. Okay, so it's around that, but it's not right at that. Any questions? That just nailed it for you, right?
No, not nailed it, but
Are you serious? It did clear it up?
pointed it in the more of the right way.
Okay, because I thought you were being silly. No, good. That's awesome. Okay, so that was the 1s orbital. The 2s orbital, the 3s orbital, 4s, all the s orbitals are spherical. Okay, they're ball-shaped. 2s and 3s, they're larger than 1s. And so the average distance, or that most likely radius, is longer. The electrons are farther from the nucleus. But these orbitals contain at least one node. So here's an illustration of a standing wave. And you can make a standing wave with a piece of string or a spring. And I'm going to show you a video in just a minute. But you get a standing wave, and it will have nodes in it. So the node is where, if you think of this as a spring, or let's go with string going up and down. At the node, there's essentially 0 probability. And here, where it's going up and down more, you have a higher probability. So when you look at a standing wave like this, it's blurred, right? Because it's moving so fast, it's blurred. And so in a sense, that's like the electron. You can think of the orbital as this blurred standing wave. If you stop this, you might find the string here, or here, or here. You would, a flash photograph freezes it in time, right? And you would see that it is in one discrete place. But when you just look at it while it's moving, it seems to be within the whole volume. Does that make sense? I think that's the best way to get a beginning understanding of what these electron orbitals are. Let's stop here and look at the video.